Right then, so moving on to our next category or classification of differential equations, we've got linear ODEs. So 1.4 is called linear equations and the integrating factor. So we've got differential equations, and that breaks down into ordinary differential equations and partial differential equations. Ordinary differential equations, for right now we're just working with first order. ODEs. And there was a classification called separable. And that was the topic of the previous lecture. The topic of the current lecture is first order linear ODEs. And so that's what we're talking about today. So before we get into it, let me give you an example. Suppose you had something like y prime plus 6y equals e to the x. Let's recognize that there is absolutely no way that you could rewrite this so that y prime would be equal to a function of x times a function of y. So it's not separable. So we need some other technique for dealing with this. Before we get into that, though, let's talk about what the word linear means, because we're definitely going to need to at some point, so we might as well start now. So, just some terminology. First of all, definition. Given a positive integer I, the ith order differential operator is the operator that takes the ith derivative of a function. Okay. And by operator, what I mean is so a function takes a real number and gives you a real number back. An operator takes a function and gives you a function back. And then also, let's establish the convention that the zeroth derivative of a function, which looks like d0f dx to the 0, this is just f. That's our definition of the zeroth derivative. Okay, so another definition. Let f1, f2, fn be mathematical objects. and let S be a set of mathematical objects. If you take linear algebra, you'll learn that this doesn't have to be as broad as just mathematical objects. It just has to be something else. But for now, let's just say any mathematical objects whatsoever. A linear combination of f1, f2, fn with coefficients in S so that's the term that we're trying to define, is any expression of the form S1 times F1 plus S2 times F2 plus plus Sn times Fn, where S1, S2, Sn are elements of S. Okay. So, for us, these f's are going to be typically functions or occasionally vectors. To look at some examples, if you have something like 5 cosine x plus 3 sine x, this would be a linear combination of the functions cosine x and sine x with coefficients in the real numbers, because 5 and 3 are real numbers. You could have something like x to the fourth minus 3x to the third plus 6x squared minus 2x plus 1. That would be a linear combination of powers of x with constant coefficients, because x to the 0, x to the 1, x squared, x cubed, and x fourth are all powers of x. And these coefficients are all constants. 1, 2, 6, 3, 1, or negative 3 and 1. And in fact, every polynomial is a linear combination of powers of x. Okay? So this is all a linear combination is. I just needed a term for when you take a bunch of things, multiply them by constants, and then add all those things up. So, next definition. A linear differential operator is a linear combination of basic differential operators with functions of x as coefficients. So again, oh, this should say ith order basic differential operator. Sorry about that. So a basic differential operator is just take the something derivative. A linear differential operator is when I say, all right, take a linear combination of those operators. So this might look like something like L equals x squared second order basic differential operator minus 2 to the x first order basic differential operator plus 3 first order or zeroth order basic differential operator. Okay. And then, based on all of this, a linear ODE is an ODE of the form L of y equals Q of x, where L is a differential operator or linear differential operator, whatever I called it. Yeah, linear differential operator. Sorry, let me actually fix that. Linear differential operator. And Q is any function of x. Okay. So the ordinary differential equation that I showed you before, y prime plus 6y equals e to the x. This is an example of a linear ODE. It's an example of a linear ODE because it's because if you break this down, you can think of first order basic differential operator plus 6 zeroth order basic differential operator. This is acting on y to give us derivative of y plus 6y, and then that's being set equal to e to the x. Okay. In other words, a linear ODE is one in which you have y and its derivatives set in a linear combination equal to another function. So another example of a linear ODE could be something like y prime prime minus 6y prime plus 2y equals 0. That's a linear ODE because it's taking a linear combination of y and its derivatives and setting it equal to a function. You could have something like xy prime minus x squared y equals 0. Again, it's a linear combination of y and its derivatives being set equal to a function. You could have something like third derivative of y minus 6y prime prime plus y prime minus 6y equals sine x. Again, taking linear combinations of y and its derivatives and setting it equal to a function of x. And again, just to refresh our memory, this is a first order ODE, a second order ODE, a first order ODE, and a third order ODE. Okay. Some examples of ODEs that are not linear could be something like when you have y times y prime. That's nonlinear because it's not a linear combination of y and its derivatives. You could have something like y prime squared equals y. Again, not a linear combination of y and its derivatives. You could have 1 over y prime plus 1 over y equals x. And once again, not a linear combination of y and its derivatives. So these are all nonlinear. So let's talk about how to solve a first order linear ODE, because that is going to be the point of today's lecture. In general, every first order ODE that you'll ever be given, every first order linear ODE that you'll ever be given will be some function of x times y prime plus some other function of x times y equals some other function of x. Right? Because it's a linear combination of y and its first derivative being set equal to a function. The first thing that you have to do is put it into a standard form. By dividing by the coefficient of y prime. So you get y prime plus some function of x, which I guess we'll call p0 of x, times y equals another function of x, which we'll call, I guess, q0 of x. Okay. So now that you've put it into the standard form, you need to define what's called the integrating factor of this ODE. I denote that by rho of x in my notes. However, rho looks too much like p, so I've learned from teaching this class that students will prefer that I use a different Greek letter for it. So let's call it mu. Mu of x is defined as e raised to the integral of p0 of x. Well, I say e raised to the integral. What I really mean is e raised to any antiderivative of p0 of x. Okay? What you do is you multiply this by everything. You get mu of x times y prime plus p0 of x times mu of x times y equals mu of x times q0 of x. Okay? Now what you've done here is you've rigged the situation so that this left-hand side will end up being the derivative of the integrating factor times y. In order to see how this works, let's look at some examples. So let's suppose we're going to try to solve y prime plus xy equals x. And by solve, what I mean is find its general solution. All right, well, it's actually already in the standard form. Standard form just has y prime with a coefficient of 1, and that's exactly what we have here. So we can just define the integrating factor. Integrating factor, by definition, is e raised to an antiderivative of the coefficient of y. In this case, the coefficient of y is this function x. So we're just going to raise e to an antiderivative of x. Well, what would be a suitable antiderivative for x? How about 1/2 x squared? So e to the 1/2 x squared. All right. Next up, we're going to multiply this by the entire standard form. So we're going to have e to the 1/2 x squared times y prime plus x e to the 1/2 x squared times y equals x e to the 1/2 x squared. Okay, now, I think the next step is what students find to be the hardest part of solving these ODEs. This left-hand side is in fact the result of a product rule. What I mean is that if you take the derivative of the integrating factor times y, in this case that's e to the 1/2 x squared times y. Well, you have to use the product rule to compute that, right? So you have the first times the derivative of the second, so that's e to the 1/2 x squared times whatever the derivative of y is, and then add to that the second times the derivative of the first, so y. Then you have the derivative of e to the 1/2 x squared is e to the 1/2 x squared multiplied by x. Does that look familiar? Because that is exactly our left-hand side. Okay? So what this means is that we have rigged the situation so that the left-hand side just ends up being the derivative of the integrating factor times y. Okay? And that means this left-hand side is equal to this right-hand side. So x e to the 1/2 x squared. All right, and at this point, we're just solving for y. Well, we were always solving for y. But at this point, there's hopefully what you can see to be an easy way to do that. To cancel this derivative, we have to take the indefinite integral of both sides. So we'll get e to the 1/2 x squared y equals the integral of x e to the 1/2 x squared. This right here is an integral that you can do by u substitution. So here you want to say u equals 1/2 x squared. In that case, du ends up being just x dx. So then this becomes the integral of e to the u du. An antiderivative of e to the u would be e to the u. So we have e to the u plus c. And then u is just a name for 1/2 x squared, so what we get here is e to the 1/2 x squared y equals e to the 1/2 x squared plus c. Divide both sides by e to the 1/2 x squared, and what you get here is y equals 1 plus c e to the negative 1/2 x squared. And that's our general solution. Okay. So they always work like this, linear ODEs, first order linear ODEs. You put it in standard form. You find the integrating factor. Multiply the integrating factor by everything, and then the left-hand side is now rigged so that it will be the derivative of the integrating factor times y. From there, you take the integral of both sides and solve for y. Okay. Why don't we do another example? This one will make it an initial value problem. This one looks like x squared y prime plus xy equals 1. With the initial condition, y of 1 equals 3. So this is our initial value problem. All right, so again, this is a linear first order ODE because it is a linear combination of y and its derivative being set equal to a function of x. So we can definitely use the method of the integrating factor here. First thing we've got to do though is put it in standard form, which means divide everything by the coefficient of y prime. So divide everything by x squared. We'll get y prime plus 1 over x times y equals 1 over x squared All right, now we are ready to define our integrating factor. The integrating factor, mu of x, is e raised to an antiderivative of the coefficient of y. In this case, the coefficient of y is 1 over x, so we're taking an antiderivative of 1 over x. Well, a perfectly suitable antiderivative for 1 over x would be ln x. And then if you raise e to the ln x, you just get x. So you multiply this by the entire standard form. You multiply everything by x. You get xy prime plus 1 times y equals 1 over x. And at this point, if you look at this left-hand side, you realize this is just the derivative of x times y. The integrating factor times y. So that's 1 over x. All right, so then in that case we can cancel this derivative by taking the indefinite integral of both sides. We'll get xy equals the integral of 1 over x dx. Now, an antiderivative of 1 over x would be ln x, so xy equals ln x. And there better be a plus c in here somewhere, right? And so finally, to solve for y, we just need to divide both sides by x. So we just get y equals ln x plus c divided by x. And that is our general solution. Oh, wait a second. That's the general solution, but that's not the answer to the problem, because we have an initial value problem. So we're not quite done yet. There's one more thing that we have to do. We have to figure out the value of c. Picard's theorem says that there will be exactly one value of c that makes this initial value problem work, but we still need to figure out what that is. So, 3 is y of 1. And according to our general solution, that's going to be the natural log of 1 plus c divided by 1. The natural log of 1 happens to be 0. So we have just c divided by 1, which is c. Therefore, c equals 3, which means that we are looking at the function y equals ln x plus 3 divided by x. And that is the particular solution that solves our initial value problem. Let's do another one. This one is going to be another initial value problem. This one is y prime plus cosine of x times y equals 2 cosine of x, with the initial condition that y of pi should be 5. Right, so this ODE is already in standard form because 1 is the coefficient of y prime. So we can define our integrating factor. Mu of x equals e raised to an antiderivative of the coefficient of y. In this case, the coefficient of y is just cosine of x. So we need an antiderivative of the cosine of x. Well, how about the sine of x? So e to the sine of x is our integrating factor. We multiply this by everything in sight, and we get e to the sine of x times y prime plus cosine of x times e to the sine of x times y equals 2 cosine of x e to the sine of x. The left-hand side is already rigged so that it will be the derivative of the integrating factor times y. And then that is equal to 2 cosine of x e to the sine of x. You take the indefinite integral of both sides to cancel that derivative operator. You get e to the sine of x, y, equals the integral of 2 cosine of x, e to the sine of x. That is another u substitution problem, because if you set u to be sine of x, du ends up being cosine x dx. Therefore, we get here e to the sine of x times y equals the integral of, let's see here, 2e to the u du. Now an antiderivative of 2e to the u would be 2e to the u. So we have e to the sine x y equals 2e to the u plus c. U is a name for sine x. So this becomes e to the sine x y equals 2e to the sine x plus c. Divide both sides by e to the sine x, and we get y equals 2 plus c e to the negative sine x. And that is our general solution. To find the particular solution that solves the initial value problem, we just have to say 5 equals y of pi, which in this case is going to be 2 plus c e to the negative sine of pi. The sine of pi is 0. E to the 0 is 1. So we have 5 equals 2 plus c, and therefore c equals 3. So the particular solution that solves our initial value problem is y equals 2 plus 3 e to the negative sine x. All right. Again, nothing new happening here. You put it in standard form, you define the integrating factor, multiply it by everything, the left-hand side is rigged to become the derivative of the integrating factor times y, and then we can solve for y. All right, let's look at another example. Let's suppose we're trying to find the general solution of y prime equals x minus 2y. Okay, again, I shouldn't have erased the standard form, but the standard form is y prime plus a function of x times y equals another function of x. Okay, this has the quality that 1 is the... Sorry, this has the quality that 1 is the coefficient of y prime. However, the standard form also requires that y prime and y be on the same side of the equation, preferably the left. So, what you need to do is first add 2y to both sides. We get y prime plus 2y equals x. Now you can define the integrating factor. Mu of x equals e raised to an antiderivative of the coefficient of y. In this case, the coefficient of y in the standard form is 2. An antiderivative of 2 would be 2x, so this is e to the 2x. Multiply this by the entire standard form, and we'll get e to the 2x times y prime plus 2e to the 2x times y equals x e to the 2x. This left-hand side is once again rigged to be the derivative of e to the 2x times y. So we can take the integral of both sides. E to the 2xy equals the integral of x e to the 2x. Now that right there is a quintessential integration by parts integral. Specifically, you have to set u to be x and dv to be e to the 2x dx. In that case, du is dx, and v is 1/2 e to the 2x. So the right-hand side, we have e to the 2xy on the left-hand side. The right-hand side turns into uv minus the integral of v du. So we have 1/2 x e to the 2x minus the integral of v du is going to be 1/2 e to the 2x dx. And then you do this antiderivative and you get e to the 2x y equals 1/2 x e to the 2x minus 1/4 e to the 2x plus c. Divide both sides by e to the 2x, and what we get here is y equals 1/2 x minus 1/4 plus c e to the negative 2x. And that's our general solution. There are other ways of writing it too, but that's just one. All right, and let's look at one more example. This one is xy prime plus 2y equals 5 root x. Alright, so first things first, it's not in standard form. It's not in standard form because 1 is not the coefficient of y prime. So you divide everything by x. We get y prime plus 2 over x, y, equals 5. X to the 1/2 divided by x is going to be x to the negative 1/2. And so that is our standard form. So we can define the integrating factor from here. Mu of x is e raised to an antiderivative of the coefficient of y. The coefficient of y here is 2 over x. So we have this. A perfectly valid antiderivative of 2 over x would be 2 ln x. So we have e to the 2 ln x. That can be rewritten as e to the ln of x squared. And so we're looking at x squared as our integrating factor. All right, multiply that by the entire standard form, and what you're going to get here is x squared y prime plus x squared times 2 over x is just going to be 2x, y, equals 5. X squared times x to the negative 1/2 is going to be x to the 3/2. The left side is rigged to be the derivative of the integrating factor times y, so in that case it's going to be x squared times y. And this is 5x to the 3/2. Take the integral of both sides, and now we're working with x squared y equals the integral of 5x to the 3/2. Well, if we add 1 to the exponent and then divide by the new exponent, you're going to get 5/2 as the new exponent. Divide by 5/2, you get 2x to the 5/2 plus c. And then finally divide both sides by x squared, and you get y equals 2x to the 1/2 plus c, x to the negative 2. Because 5/2 minus 2 is just 1/2. And that is our general solution. Okay? So again, same thing. Put it in standard form, define the integrating factor, multiply it by everything, and then you've got an equation that you can solve for y. All right? So that does it for today. See you in the next one.